Well, last but not least, let's talk about the requirements to sample quality and normality requirements, meaning how to take a sample. So everything that we have discussed so far, all this hypothesis testing, confidence intervals, and so on and so forth, will be trustworthy. So we can trust them. So they indeed will show the things that we expected them to show. You remember that when you take a sample and when you get the measurements and get some statistics of your sample, you have a lot of uncertainties. Where these uncertainties come from? Well, one source of uncertainty we already know, it's a sampling. When we take a sample, it's approximation of our population, so it does not represent the population precisely. So therefore, the statistics of your sample will be around the population parameters, right? And then you can think that usually sample is something small. Like in this case, you can see I have 6 apples, but the population is huge. It can be a very large garden with thousands of trees, of apple trees. So therefore, very often, and we will discuss it in this video, sampling must be carried out as a multi-step process. So instead of taking the 6 apples from the whole garden, you should take, for example, 100 kilos of apples and then reduce it until you get the 6. So sampling is one of the sources of these uncertainties, and usually it's one of the biggest sources, because when you take a sample, especially a small sample, it can be very different from the population. So that's one source. The second source is a preparation, right? So when you prepare, so you take every individual of your sample and then you do something with this individual in order to get the measurements. For example, you can grind it, you can dissolve it, and then you can, for example, reduce the volume of the liquid where you have the dissolved sample down to the volume which is acceptable by the machine, right? So that's the preparation. And then you have the measurement itself, and you just put usually we call this part is aliquot. We put this aliquot to an equipment, and then you get the number. So all these 3 are sources of errors. But usually the machines are very well standardized, and then they usually have the smallest source of error. Many methods have very straightforward preparation procedure, and if you follow this procedure, if you follow the guidelines, then you can minimize the preparation error. Of course, we are humans and we still can make some mistakes, but anyway, so there are strict rules about how to prepare and also how to measure your values, right? Your characteristics of your sample. Usually it's very little information given about how to take a good sample, how to reduce these uncertainties on this step, how to reduce uncertainties that comes from sampling. And that's exactly what I'm going to talk about in this video. Well, you remember that this is the whole procedure that we have. So first we take a sample, and that's what we call sampling. Then we use descriptive statistics to describe the sample, and then we use inferential statistics to generalize knowledge about your sample to the whole population. We discussed already this part and this part a little, but we haven't discussed this part, sampling, how important sampling is. Because if sampling is bad, then your statistics, all your calculations, of course, even if you've done everything correctly, you cannot trust them, because they will simply do not reflect the truth, because your sample actually does not represent the population well. By the way, in this example, you can see that my sample is not representative sample, because, for example, in this case, in the population, I have also these green circles, but I don't have any green circles in the sample. So therefore, if I look at this sample, and if I try to generalize the information from the sample to the whole population, in this population, the green circles would not exist. Okay. So the idea is following. We have a population, and we have some characteristics of this population, which is described by given parameters, especially if it follows the theoretical distribution, like normal distribution or any other distributions. Then we take a sample, and then we get the statistics of this sample. And the idea is we need to get a sample. So when we use inferential statistics and make an inference either way, right, and make an inference, this inference should reflect the truth. For example, if you compute 95% confidence interval, indeed 95% of the samples will contain the true population, for example, average inside. So how to take a sample for which all these statistical methods that we have learned so far will indeed work. Okay. Well, the idea is following. Sample should be random and representative. Representative sample, it's a sample which is big enough to represent the whole population. For example, in the previous example with color circles, my sample was not representative. If you toss your coin 4 times and get 4 heads, your sample will not be representative because having a tail in this sample is not considered at all. Okay, so sample should be big enough to represent the whole population, and that's what we call a representative sample, right? So statistics of this sample should be close to the parameters of the population, and at least by making an inference, you can estimate the parameters of population correctly. One of the ways to get a representative sample is to make it random. What it means? It means if you think about every individual object in the whole population, or maybe it can be not physical objects, but every reaction run or every observed phenomenon and so on and so forth, every object in this population should have equal chance to be taken as a part of your sample. So that's what we call a random sample. Okay. If sample is not random, then we call such sample as biased. For example, if you want to, to say something about average salaries of chemical engineers in Denmark, and if you ask engineers around Copenhagen and do not ask engineers that work in other parts of the country, then of course your sample will be biased because usually in Copenhagen we have higher salaries than in the other parts, right? So that's the overall idea. And then the sampling, it's the procedure of taking a sample, right? So it's a procedure of taking these individual objects from the population. Now, how to get a good sample? There are some relatively simple rules, and if you follow these rules, you can get indeed random and representative sample. I recommend you either to order a book or maybe to get it in the library. There is a nice book from Professor Esbensen that is called Introduction to the Theory and Practice of Sampling. Or you can use a lot of free resources like, for example, sampling columns in Spectroscopy Europe, which Spectroscopy Europe, it's a journal, it's a magazine actually, which contains a lot of popular articles about how to get a good sample and so on and so forth. And then you can also find a lot of nice overviews, reviews, in the other scientific journals. For example, this one is, as far as I remember, from the Chemolab, the Chemometrics and Intelligent Laboratory System journal. Okay, so please use this link to get a little bit deeper understanding of what theory of sampling is. I'm going to tell you very, very brief, very, very basic things about how to get a good sample. Well, first of all, instead of these 2 steps, sample population or population to sample, in fact, the reality is a little bit more complicated. At the beginning, we don't have access to the whole population. If you want to invent a medicine against a particular form of cancer, then your population is all patients that have this particular form of cancer right now, right? Or maybe in future. Of course, you cannot have access to all these patients. Usually, your access is limited by 1 or 2 hospitals, right? And this part of population that you can actually take your sample from, we will call a lot, okay? So lot, it's a part of population which you take a sample from. And then when you take a sample, it's a good idea to take it in several steps, like I said already before. First of all, you take a bulk sample, which is way larger than the sample that you need. Then you reduce and reduce and reduce its size until you get a laboratory sample, which is small enough to go to laboratory, to take it to laboratory. And then you prepare the aliquots based on the laboratory sample. This is how it looks like with the apple. So you have apple garden, which is a lot. And then bulk sample can be like a very, very big box or several boxes of apples taken from this garden, which you reduce down to, for example, 6, 10, 15, 30 apples, which you can work in laboratory with. And then you prepare an aliquot from each of these individual objects. So that's the overall idea. When you take a sample from the lot, it's very important to consider what dimension your lot has and what it means. Usually all lots have 3 dimensions if we talk about geometrically. But from the sampling point of view, the dimension can be different. Let me show you an example using a coal. For example, you want to assess a quality of coal, and then you need to take a sample. So in this case, you can see like a hip, and this dimension is 3D. Not because it's geometrically 3D, but also because you cannot take a sample. You need to take a sample from 3 directions. So you need to take a sample from this direction. So you cannot take all of this. You can take, for example, this part, this part, this part, and this part, right? So that's what we call a sample. And then you need to take a sample in this direction also. For example, this is already 2D. But you can also, it also has a height or depth. So you also need to think about at which depth to take a sample. Apparently, what you have in the bottom will be different from what you have on the top, right? So in this case, it's very complicated because you have to sample from different directions, along different directions. What you can do, you can distribute this big amount of coal as a kind of 2D. So in this case, you can tell me also it's not 2D, it's 3D. Yes, but you don't need to sample from the depth because depth is quite small. So you can sample, you don't need to sample, you can take the whole, right? So in this case, you need to sample only in two directions like this. For example, that will be your sampling points where you take a small portion of coal from, and that will reduce the amount of your load, for example, 10 times smaller, make it 10 times smaller, then you will reduce it again and again and again. So this is 2D dimension of the load, right? And then finally, this is 1D when you have a conveyor belt. Again, we don't have 3D, we don't have 1D geometrically because you still have a width and then you have a depth. But the width and depth are small, so you can take the whole part of it. So you need to sample only along one dimension. That's why it's called one-dimensional load, okay? So in this case, you have like a 3D, and all three dimensions are big enough. So you need to sample, for example, here, 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 and so on. So you need to sample in 3D. That's the most complicated thing. Here you have 2D. So you need to sample along two dimensions. And then finally, here you have 1D, where you sample just along one dimension, either random sampling or systematic sampling, and that makes your life much easier. So the first step, which you can consider, is how to reduce the dimension of your load from 3D or 2D to 1D. The smaller, the better. Okay. So this is just an example how to take a sample from this conveyor belt. You can see they use a special device, so you can take the whole portion. So you don't need to sample along this direction or along this direction, right? They take a whole, so they need to sample only along one dimension. Okay. This is just another example. In this case, it's also taken from one of the Professor Kim Esbenson book. They analyzed the quality of bark, and then you can see that what they did, they took a lot of bark, and then they distributed like a small sausage here, right? So they reduced the dimensionality of this lot, like from 3D to 1D, and now they can just take random sample along one dimension. You can see it's randomly taken, right, portions. And that will be the random sample from one-dimensional load. Okay. The second very important thing is homogeneity and heterogeneity. If your load or bulk sample is heterogeneous, then taking small portions of this heterogeneous load or heterogeneous bulk sample will end up with very different individuals, with very different portions. But if you mix everything, if it's possible, of course, before you do the sampling, so if you increase homogeneity of your sample, then you can see that they will be statistically very similar to each other. And that reduces the uncertainty a lot. So homogeneity is a very important thing. If you can homogenize your load or homogenize your bulk sample, please do that because it will help you a lot to reduce the uncertainty of your sample. Okay. And this is the overall procedure, right? So you can see that, first of all, you need to reduce the dimensionality of your load, if possible, of course. We have different situations, right? So in this case, you can see that indeed my load has just one dimension. I mean, it's 3D geometrically, but I can sample along one dimension. Then take a random sample. That's what I do here. You can see that's my random sample. Position of these sampling points are taken randomly. Then increase homogeneity. How? I blend it, I mix it, and then repeat it again. So it means that this little heap will also be making a sausage, then it will take a small portion of each, then you mix it, and then until this size of these individual portions is small enough to be taken to laboratory. So that's one of the simplest way to get a random and representative sample from your population, or better say, from your load. And I can show you a lot of examples why sampling is important. Just one example I took it from this paper from Cell Reports 2020. What they did, they actually analyzed how sampling can influence the classification of different tumors. So in this case, they analyzed intratumor mutation burden, TMB. And the idea is following. So the normal procedure is they take an issue, And then from this issue, they take 3 random points, sampling points, and that's your sample. So they analyze every individual, and then they end up with some biomarker data, which they use for classification, if that, for example, malign tumor or benign. Yeah. But what they did instead, so in addition to that, they took the residuals. So you can see that you have 3 holes here, yeah? And then they homogenize it. They homogenize it thoroughly. They make this mass reduction, so they reduce the mass of this. And then they got another 3 samples, which were like much more homogenized. And then they repeat the procedure. So again, they got some biomarkers data from this. Now look, for example, for the lung tissues, when they use the standard procedure, the amount of misclassified cases was 20%. When they use the modified procedure, which is based on the theory of sampling rules, it was reduced down to 2%. Look, from 20 to down to 2%. Okay, and then for the bladder tissues, the misclassification rate using the original procedure was 52%. They reduced it down to 4%, just by using the correct sampling, without using any sophisticated machine learning techniques, no artificial intelligence, nothing. Just the correct sampling can increase the quality of your results tremendously. So please pay attention to sampling. And it's very important for statistics as well, because if your sample is bad, then statistics will not show you the results that you can trust. So once again, in order to trust your statistical analysis, your sample should be random and representative, and pay particular attention to your sampling procedure in order to achieve this. Okay. So this is kind of a summary about hypothesis testing. I have a lot of text, but I will just make it very brief. So remember that, first of all, when we do hypothesis testing, we have a default assumption about the population our sample came from, and that's what we call a null hypothesis. We define null hypothesis as something that most expected based on our previous research, previous investigation, maybe observations from other researchers, and so on. Then we also define an alternative hypothesis, which is like something that is, we take, if null hypothesis, we don't have any evidence that supports our null hypothesis, we take an alternative hypothesis. Any test results in a p-value, and p-value is a chance to get a sample as extreme as you have related to the null hypothesis, or more extreme, assuming that null hypothesis is indeed correct. So p-value is nothing but measure of extremeness, how extreme your sample is for this particular null hypothesis. And then if you need to make a decision, if you don't need to make a decision, you just report the p-value and then make your conclusions based on this reported p-value. But if you need to make a decision, if you need to use this test like a bifurcation point, so you need to take a decision after you got the test results, then you do it like this. You compare p-value with a threshold, which we call the significance level, and then depending on these comparisons, you take one of the 2 procedures, right? Significance level must be defined before you actually take before you actually start the experiment, right? Before you actually take a sample. So at the very beginning, when you design your experiment, when you design your research, you need to discuss with your, for example, colleagues, which significance level to use, why you should use this significance level, what kind of constant pros it has, and then fix it and never change. Okay. And then you remember, most important thing, sample must be random and representative. So invest some time in order to develop the correct sampling procedure. Then one last thing, it's the normality requirements. You remember that when we start talking about the sampling distribution, about t-distribution, about normality of the means and so on and so forth, we assume that the sample is normally distributed. Okay. So central limit theorem says is, if you take, for example, random numbers, like several random numbers, okay, the sum of these random numbers and so on will be normally distributed if this amount of these random numbers approach infinity. In fact, if these values are normally distributed, then this central limit theorem works for any n. So it will work for any number of samples, even if you have 2, sum of 2 normally distributed random numbers as random numbers. But it also works if population is not normally distributed. And that's the cool thing. So it means that average almost always normally distributed, regardless which population you have. However, in this case, your sum should be big enough. So it means that the number of items in your sum should be big enough. Ideally, it should be close to infinity, but in reality, it starts working even if you have like 30 or more. So therefore, it means that if your sample is large, 30 or more, you don't care about normality. You can use t-test just as is. You don't need to check the normality. Also, it's a good idea to do anyway. But if your sample is relatively small, then you need to check the normality, because you cannot trust the t-test results if your sample didn't came from normally distributed population. Okay, so this is kind of some practical rules. So if your sample size is 30 or larger, then you don't need to check the normality. You can use t-test and trust it. Also, it's a good idea to do that anyway, because it provides you a lot of information about your sample, right? If your sample size is between 30 and 6, then please check the normality before. So use QQ-plot and normality test, for example, Shapiro-Wilk test, like we learned in the block number 1, and make sure that your sample came from normally distributed population in order to use t-test. Okay. If it didn't, then you need to use non-parametric statistics, which we are going to talk about, and non-parametric methods, which we are going to talk about in the last block number 4. Okay. What happens if your sample size is even smaller, like 3 or 4 measurements? In this case, the checking normality will be very difficult, because you will not have enough power for this sample size. So therefore, you either have some strong a priori assumption about normality. For example, you already took samples, bigger samples from this population, so other researchers did, or maybe understanding of physics and biology and chemistry of your population, you understand that this this population values indeed follow normal distribution. So you need some a priori knowledge. So in this case, you also can apply a t-test. So that's it about some basics of hypothesis testing. And in the next learning sequence, we will discuss how to use hypothesis testing for comparing 2 or more samples which came from different populations.